we learned about momentum, what momentum means, why we need quantity, momentum. Remember, I told you that, yes, you can set an object into motion by applying some force on it. But after you cut the contact between the force and the object still continues to moving. And this motion, even if you cut the contact, can be explained by the concept of momentum. So when some force acts on an object, this force causes this object to gain some linear momentum. And with this linear momentum, object continues to moving. Same thing happens in angular rotational motion, but this time torque, we need torque to start the rotation. When you apply some torque on an object starts the rotation. But when you cut the contact between the torque and the object still continue to rotate. So we explain this rotation by angular momentum. We say that, yes, initially some torque acts on this object, and this torque causes this object to gain some angular momentum. In fact, in physics, we have two equations. One of them you studied last year. It was this relation between the force and linear momentum. Yeah, if some net force acts on an object by some time interval delta t, which you said last year impulse causes some change in the linear momentum of the object. And in fact, this equation has a equivalent equation in rotational motion, but this is studied in the 11th grade, but this equation will not be studied in the 12th grade. However, equations are very similar. Remember, rotational analog of force is torque. If some torque acts on an object by some time delta t, causes this object to gain some angular momentum delta L. In fact, these two equations are also very similar. Yani, if a net torque produced on an object's angular momentum changes. So to give an angular momentum an object, you need to produce some torque initially on the object by some time, so then this object gains this angular momentum, and then after that, even if you cut the connection between the source of the torque and the object will continue rotating with this angular momentum it gained before. As I said, this equation is not in your book, but this equation will help us to understand the conservation of angular momentum. What does conservation mean? First, let's get this. Conservation is if you keep a physical quantity constant. So we say that this quantity is conserved. You studied one part of them in the 11th grade as conservation of mechanical energy. We are going to also study in this section. So if mechanical energy of an object is kept constant, so we say that this mechanical energy, this energy is conserved. Or also you studied, maybe you remember or not, you studied in the electrostatic chapter, conservation of electric charges. You also studied that one. And now we will continue with the conservation, but with time we are going to talk about conservation of angular momentum. Only angular momentum is conserved? No, linear momentum is also conserved. Last year we studied this part. So what is the last year part? This part is when I talk about translational motion, it's about 11th grade. So then I will make connection to the 12th grade. So it was like this last year. When the net external force acting on an object is zero. Yani when this force in here becomes zero, this force becomes zero. So delta P also becomes zero. And there will be no change in linear momentum. The linear momentum of the object does not change, which means linear momentum of the object, yani P stays constant. Does not change means constant. So same thing, same sentence can be written in a similar form in rotational motion. If net torque, the net external torque acting on an object is zero, yani if this torque is zero, so then which means there will be no change in angular momentum, which means angular momentum will stay constant. Does not change means stay constant, stay constant. Then I will write them, yes, angular momentum will be constant. So what is the condition? Condition is this: when net external torque acting on the object is zero, when net torque acting on the object is equal to zero, so in this case, this object's angular momentum cannot change. Its angular momentum will stay constant. This is called conservation of angular momentum. Best example is the Earth. Earth is spinning right now. Earth is spinning with the angular speed, some angular speed. This angular speed does not change because this Earth is keeping this angular momentum constant. Angular momentum constant. Yani I times omega is constant for the Earth. For that reason, so angular momentum of the object is, of the Earth is constant. Every day takes 24 hours. If an object, for example, in the future, I hope we are not going to see that, hits the Earth and then produces some torque on the Earth, so it can make some change on the angular momentum of the Earth. Maybe days will be longer or shorter depending on the impact, the effect of the impact by this space object. So this is what conservation of angular momentum is. Most important part is this: what is the condition for conservation of angular momentum? So condition is this, never forget that. Net torque acting on the object must be equal to zero. In this case, angular momentum of that object stay constant. This is known as conservation of angular momentum. Then I will continue with the next step, but this conservation has very interesting result. Remember, in translational motion, we are changing the mass. What is the rotational analog of mass? Moment of inertia. So in rotational motion, we will change the moment of inertia. Change in moment of inertia will cause a change in angular speed. So remember, we said that if net torque acting on an object is zero, external torque is zero, which means angular momentum is constant. Angular momentum is constant, which means angular momentum equation is what? I times omega must stay constant. Okay, now assume that there is a picture you see on my screen. There is a merry-go-round and there's a student. Initially, these merry-go-round students are spinning with some initial angular speed omega initial. But later, this student starts walking towards the center, towards the axis of rotation. Initially, student is moving on a circular path which is greater in radius, but after some time, this student is starting to walk on a circle with a smaller radius. Tell me, in which case student has a greater moment of smaller moment of inertia? First case, initial case, or final case? As r decreases, moment of inertia of the student also must decrease. Okay, a moment of inertia decreases. If moment of inertia of the system decreases, because angular momentum is constant, angular speed also must increase. So they are inversely proportional according to the law of conservation of angular momentum. As moment of inertia of the system decreases, angular speed of the system increases. When you make a system's moment of inertia smaller, so angular speed of this system will increase to keep the angular momentum constant. Even their ratios are equal. Yani as I decreases by 2, angular speed must increase by 2 to keep it again constant. It is very similar to required torque. And these two will simplify. Again, you will get I times omega. If angular moment of inertia decreases by 3, angular speed must increase by 3. If moment of inertia decreases by 4, angular speed must increase by 4 to keep the angular momentum constant. Okay, now you will see a movie about that. After that, let's talk about it. Let me take your question. This is a good movie. How moment of inertia causes a change in angular speed according to conservation of angular momentum. It is a very good example how changing moment inertia changes the angular speed of an object. Follow it.
This is a Hoberman sphere. You can expand it and contract it using this string.
So by extending and contracting, what are we changing in here? When it is extended, it is the very large distribution of the mass is far from the axis of rotation. When it is contracted, distribution of mass is closer to the axis of rotation. So when it is extended, moment of inertia is greater. When it is contracted, moment of inertia becomes smaller. So then this man will give initially some angular momentum by applying some torque, then release it. After that, he will change the moment of inertia, see how angular speed changes.
What I'm going to do is to use it to demonstrate the conservation of angular momentum. The axis, I'm going to rotate it about this vertical axis, and that axis is also denoted by the string that passes vertically through the sphere. We will note first that the moment of inertia in this expanded configuration is much larger than the moment of inertia in this contracted configuration. So what we can expect is that if we give it some angular momentum in the expanded high moment of inertia configuration, and then we contract it, its angular speed should increase. And sure enough, it's one of the most spectacular demonstrations, I think, of conservation of angular momentum.
Okay, this is one of the good experiment, but also we have another application of conservation of angular momentum, especially ice skaters are doing that. Now look at this ice skater, watch him. Initially his arms and legs will be open, and after that he's going to close his arms and legs. See how he's changing his speed without applying a torque, according to conservation. Okay. So then, this is the two good examples about the conservation of angular momentum, which means if you decrease the moment of inertia of a system, angular speed of that system increases, or vice versa. If moment of inertia of the system increases, so angular speed of the system must decrease to keep the angular momentum constant. Okay, so this is what's conservation of angular momentum in the equation. Left part is, as I said, is the linear momentum conservation. As I said, it's 11th grade part, which is mass initial linear momentum, final linear momentum must be equal according to conservation of linear momentum. Initial linear momentum, mass initial, speed initial, final linear momentum, mass final, speed final must stay constant. But in angular form, in rotational motion, we have angular momentum. So the total angular momentum before of the system before interaction. Interaction means, I mean, when he opens his arm or closes his arms, and when he makes some change on the system. So that's the interaction I am talking about. The total angular momentum of the system before interaction or total angular momentum of this after interaction must equal to each other. Yani initial angular momentum and final angular momentum must be equal. Initial angular momentum is I initial times omega initial. Final angular momentum is I final times omega final. These two must be equal because must stay constant, never change. If net torque, of course, the condition is what? Net torque acting on this object must be equal to 0. This is the condition for angular momentum. Okay, now I will start solving problem. Page 132. This is the sample problem. In fact, a part of this problem we did before, sample problem part. So I will start solving this problem 132. Sample problem 2D. A 65 kilogram student is spinning on a merry-go-round that has the mass of 5.25 times 10 to the power of 2 kilogram, which means 525 kilogram, and the radius of 2 meters. She walks from the edge of the merry-go-round towards the center. If the angular speed of the merry-go-round is initially 0.2 radian per second, what is its angular speed when the student reaches a point 0.5 meter from the center? So now, in fact, if you refer to the previous videos, these two videos, in here, what's changing? Angular momentum of inertia increases or decreases when the student walks towards the center? Okay, if student walks towards the x rotation, I mean from this position to that position, from this position to that position, moment of inertia decreases, and so angular speed must increase. They are inversely proportional according to law of conservation of angular momentum. But I will find it. How much? It is greater than 0.2, but how much is this? Now I will calculate that. So this system has two components. Every system in this section, this title will have two components. One component in here is the merry-go-round. Second component is the student. So I want you to record the given of these two components one by one. So first component is, as I said, the merry-go-round. I will separate them. Merry-go-round has a component, has a given mass. How much is the mass? 525, capital M. One mass will be greater in number than the other one. That's why that mass, write capital M. Merry-go-round is a greater mass, 525. That's why I will write it in capital M. And also radius of the merry-go-round is in capital I will write for it, which is 2 meters. So this is the given for the merry-go-round. But also there is a second component in this problem, which is the student. If student has a smaller mass, so I am going to write the given for the student for small letter, I mean small m, 65 kilogram. This is small m, this is small m, this is capital M. So small m is 65 kilograms. But students is more in a circular path on this merry-go-round as this merry-go-round spins. So initial radius of the circle is r initial. Then he's walking towards x rotation. That's why circle decreases. I mean, his body follows. That's why radius of the circle also decreases. So student has two circles. One of them is initial, before the interaction, before he starts to walk. Second one is after he walks. That's why I will write two radius for the student. One of them is small r initial. Initially, this student is at a distance of 2 meters because at the edge, 2 meters from the x rotation, which is equal to the radius of the merry-go-round, which is 2 meters. But then he walks from edge to the set towards the center. Okay, finally he reaches a point of 0.5 meter. This is our final, his final radius, our final 0.5 meters. And this is the given for the student, but both these merry-go-round students are turning with the same angular speed. So omega initial is given. So if the angular speed of the merry-go-round is initially 0.2, I mean, is this only merry-go-round? No, student also, because student is on this merry-go-round. That's why they will have same angular speed, both student and the merry-go-round. That's why I will write common. Common given, omega initial is common. Both have an initial angular speed of 0.2 radian per seconds. Question. Common again, what is final angular speed? Because as I said, they are turning with the same angular speed. Calculate that final angular speed. So these are the given of this problem. So two components, merry-go-round, capital M, mass is 525, radius of the merry-go-round is 2. Second component, student, mass is 65, but students body following a circular path, but the size of the circular path is decreasing. Initially reduces by 2 meters, finally it is 0.5 meters. Both have an initial angular speed 0.2 radian per second. Of course, after student walks, this angular speed of the merry-go-round student will change to a final value. I will calculate that final value. So let's go for calculation. I wrote everything, I recorded them. As I said, first you have to calculate moment of inertia because you have to apply the angular momentum unit. Because angular momentum is what? L is equal to I times omega. So moment of inertia must be calculated initially and finally. Then you can apply this equation. Which equation? Initial angular speed, angular momentum is equal to final angular momentum, which means initial moment of inertia multiplied by initial angular speed will be equal final moment of inertia multiplied by final angular speed. But first I have to calculate what is the initial moment of inertia and what is final moment of inertia of these systems, yani before and after. First component is the merry-go-round, because merry-go-round is a rigid object. Its shape is not changing. Its moment of inertia is constant. It's a disk. Let's calculate it then. I merry-go-round initial is, it is 1 over 2 mr squared. Everybody knows that disk. Check the table. 1 over 2 m. How much is m? M is 525. 525. How much is the radius of the merry-go-round? 2. But square of 2. So when I calculate them, I will get the moment of inertia of merry-go-round about the symmetry axis, which is equal to 1050. 1050 kilograms times kilogram times meter squared. This is merry-go-round initial moment of inertia. By the time, as I said, merry-go-round is a rigid object. Its shape is not changing. Final moment of inertia of after the interaction will be the same again. So I can also calculate, yes, in here, this merry-go-round will have a final moment inertia, which is exactly the same. Again, 1 over 2, 525 times square of 2. Again, it will be 1050. Result, what is the cause? Because there is no change in the shape. Moment of inertia of the merry-go-round is not changing. This is final. But student is not like this. Initially, student is at some distance. I'm in the 0.2 meter from the x rotation, but finally 0.5 meter. So moment of inertia student is changing. Okay, now what equation I am going to use for student? Student is following a circular path. So circular motion. Its body is following a circular path. That's why you are going to use an equation which is about the point mass about an axis. Yani student will have an equation I student initial mr initial squared, mr initial squared. M is 65. Initial radius is, this radius is given 2 meters in the question, because it is the at the same time the radius of the merry-go-round 2 squared. So initial moment of inertia of student is going to be 260 kilogram times meter squared. But finally, it's not same. In here, he starts following a smaller circle. That's why moment of inertia of student is now less than that one. So let's calculate moment of inertia of student final one. Again, mr squared, but our final squared. Our final squared. M is 65, but final is 0.5 squared. Final radius is 0.5. Question is written here. So it is going to be 16 kilogram meter squared. Now I calculated all all moment inertia initial and all components moment inertia final. Of course, I need to add them to get the net total moment inertia. So initial total moment inertia is merry-go-round initial plus student initial. Merry-go-round initial is 1050. Student initial is 260. When you add them, you will calculate the initial moment inertia as 1,310 kilogram meter squared. This is initial moment of inertia of the system. But finally, moment inertia decreases. But how much? Final moment inertia, again, I merry-go-round final plus I student final. Merry-go-round final is 1050, which is not changing because it's a rigid object, plus, but student moment inertia is decreasing, it becomes 16. When you add them, you will get the result as 1066 kilogram meter squared. Now I calculated them. I calculated the final moment inertia of the system. I already calculated the initial moment inertia system. Then I can use this conservation law, conservation of angular momentum. Then you are going to write the given. Initial moment inertia is 1310. You already calculated in here. Initial angular speed is given as 0.2 in the question. So final moment inertia you already calculated, which is 2066. And calculate this final angular speed. Then simplify by 1066, dividing 1066. So omega final will be calculated if you use your calculator 0.24 radian per second. This is the result what we expected, because we expected that omega final must be greater than omega initial, because momentum inertia decreases, angular speed must increase. 0.25 is final, 0.20 is initial. As you see, final angular speed is greater than initial angular speed.